Our next presenter, Branko Karakas, is an assistant professor in the Department of Civil and Environmental Engineering at the University of Michigan. His research interests include water, data, and sensors. He heads the Real-Time Water Systems Laboratory, where his group is conducting fundamental research on smart water systems. Dr. Karakas is also the founder of OpenStorm.org, an open source consortium dedicated to sharing technologies and lessons for the sensing and control of water systems. He received his MS and PhD in Civil and Environmental Engineering and an MS in EECS, all from the UC Berkeley. The title of his talk, Building Smarter Water Systems, is today, so please join me in welcoming Dr. Karakas here to the podium for presentation of his talk.
All right, everybody. How's everybody doing? Cool. Okay. I'm Branko, and today, thank you so much for the opportunity to allow me to share some of the work that our lab's been working on. So given this context of sensors and self-driving cars, the question I want to pose to you today is sort of what role are these technologies going to play for addressing some of our largest water challenges? And before we get to there, I think it's important to sort of zoom out and sort of say why are we even trying to ask this question to begin with. We're going to zoom out not as far as Mars, like just a regular helicopter, but basically here's the urban water cycle, right? The water cycle. You might see this now, like a lot of you probably learned about this in elementary school, middle school, and it sort of encapsulates how we understand water on planet Earth. So it like evaporates from the oceans and the lakes and goes up in the sky and falls down as rain. In the case of California, a lot of it comes down as snow. And basically, we've figured out as human beings how to harness this particular thing. And it's this massive natural cycle, and the thing that our group really sort of thinks about is what happens where we live, like where you are in any given day. And so it turns out that if you sort of zoom into an urban environment, what you'll see once you start digging below the ground is sort of this invisible infrastructure. And I say invisible because basically, unlike roads and bridges and buildings, this stuff is buried, basically. But it turns out that if you look, there's, even for small communities in the United States, for a small city, you can have hundreds and hundreds of miles, basically, of linear infrastructure. And so it's quite a large system, actually. And it doesn't do it justice necessarily to just say, okay, there's water underneath the ground, there's pipes that convey water. It turns out there's different kinds of water. So usually when I strike up a conversation about water to people, here's my conceptual, this is water diagram. The first thing that always comes up is drinking water. And why shouldn't it, right? Because that's the stuff that we interact with on a daily basis. And it turns out that if you take your water supply, this could be like a river, maybe it's the Colorado River or something like that. It could be some sort of lake. We want to be able to use that water for drinking, right? Turns out you can't drink water directly out of the lake. You have to do something to it, and that's usually in the form of treatment. So we built really sophisticated plants to treat this water to allow you to sort of open up that tap and drink it without worrying. So that's one type of water. Second type of water basically says, okay, I can get water into my house. I also got to get water out of my house. And that, when we flush our toilets or when we take a shower, that's got to go somewhere. And before it returns to the place where it came from, we usually want to do something, and that's also treatment, right? We want to get out all the stuff that we put into it so that when we release it back into our rivers and lakes, it doesn't harm the environment. And so those are the two types. And there's also a third one that's like the most forgotten one, I feel like. Some of you might know about it. But that deals with the following, that when you have urban environments like streets and buildings and stuff, when it rains, that water's got to go somewhere. And so what we've done basically is we've engineered systems to take that water away from cities because we don't like it sitting around, right? So that gives me sort of the three infrastructures in the United States of drinking water, wastewater, and stormwater. As Dan already alluded to, a lot of this stuff was built a long time ago. If you look at some cities, it's almost 100 years old. Okay? And I think you'd be really hard-pressed to find engineering systems that were built 100 years ago and are still operational, right? There's only a few examples, and these are some of them. And naturally, with things that were built a long time ago, you can start experiencing all sorts of challenges. And so if we just look at drinking water, any typical city, by a lot of estimates, something like 20% of treated water is lost in urban environments because of leaky pipes, old pipes, right? And you could say, okay, that's lost water, that's not good, but it's also lost energy because we use a lot of energy to treat that water and to pump that water. Similarly, when you operate these old systems and you don't do it well, you get these kind of situations that we've seen very recently in the news, like Flint, Michigan, where the misoperation of these systems causes massive public health impacts where you have lead in the system, you have all these kind of contaminants in the system, and it gets to the point where people go out and riot, right? Because in a lot of cases, water is considered to be a human right? A lot of people try to make that argument, and it shows you how a small municipal problem can very quickly rise to the federal level where people start showing up and try to figure out how to fix things. So drinking water systems are under stress. Same can be said about sewer systems. Like, I actually really, this picture is really fascinating. This is in Taiwan. okay? This sewer pipe basically clogged. It was an old pipe. It clogged. It filled up with methane gas, and something lit it, and it sparked. And this is one way how you can discover that invisible infrastructure becomes quite visible, right? You look out the window, and it's literally exploding, okay? So we're dealing with all sorts of challenges like this, and this manifests itself across all sorts of systems. And so picking up that third one again of stormwater infrastructure, I bet most of you, when you walk into the city, you see these things like a gutter, and you're like, ew, what is this? Where does this go, right? Basically, cities maintain a really complicated system of infrastructure where water goes into this gutter, it goes into a pipe, it goes into a bigger pipe, it goes into a bigger pipe, and ultimately ends up in these massive canals that get water out of our cities. Because we don't want it in our cities, we want it out. And this is actually in LA, very close. Like, if you drive outside, you'll see these systems right here. They're designed so well that within the city of LA, you can flush out the whole entire system in an hour and a half after a rainstorm. So as an engineer, I would argue, like, what a great design. That's what we teach people in class. Same token, one storm during the summer in the city of LA produces a large chunk of your annual water supply. And you're not keeping it here, you're basically flushing it out. And that's what we designed these systems to do. We didn't design it to keep it here. But again, it shows opportunities that we're sort of missing out on. And while some parts of the country are struggling with droughts, other parts are just struggling with dealing with just rampant flooding over and over. And I sort of just love this picture just because this person's casually staring at this raging flood. Don't do that, kids. Okay, be really careful. Flooding is the leading cause of natural disaster deaths in the United States. And we're not talking about like massive floods. We're talking about almost sort of nuisance flooding. You see these cars driving under the highway overpass right there. People just misjudging how deep it is. They drive in there, and this is how we get these fatalities. So it's really, really kind of rough. So again, flooding, okay? After the flood, the water's got to go somewhere. Actually, after every storm, it's got to go somewhere. And what we do with our stormwater in the United States is we flush it out. So this is a picture of beautiful Lake Michigan. And what you see is sewage just flowing into the lake after a storm. That's bad because it leads to things like this. So these are harmful algal blooms. You have them in California. We have them in the Midwest. We have them on the East Coast. They're wreaking havoc to our ecosystems. These harmful algal blooms are just no good, basically. And so you can see how we have flooding and environmental problems that are just compounding because of aging infrastructure, essentially. And so cities are well aware of this problem, and what they do is they try to fix it. They say, we got a big problem, we're going to have a big solution. And what you see right here is the tunnel in the city of Chicago. It's multiple billions of dollars. Basically, they said, the water's all going downstream, why don't we dig a really big hole and capture it? And that's how we engineer these systems. And when I went to engineering, when I first got interested in civil engineering, I saw pictures like this, and I was like, wow, that's so cool. Like, I want to build that. But I've quickly realized that nobody has the money to do this. Very few cities have the money to build large projects like this. And so what do we do in situations like this? So can we look at a more representative city in the United States? And I just happen to choose the one that's in Michigan, where I live. This is our school slogan. Shows you where the city of Ann Arbor is. For those of you looking for universities, come check us out. This is the city of Ann Arbor. And I kind of want to show you that even cities like this, which are relatively affluent, college town that's got money and a good tax base, still is subjected to flooding, right? And so the city of Ann Arbor, just like many other cities, try to combat this by building many distributed solutions. So they say, look, we don't have money to build a giant tunnel. What we're going to do is we're going to fix neighborhood by neighborhood. Okay, so we're going to build little things. You've probably seen these. They look aesthetic. They look like, they could be like, well, it's supposed to be nice, right, in the backyard, like an architect designed it. Actually, they're there for flood control. They're there to treat the water before it goes downstream. And so the city starts deploying these, right? This is like the watershed that we work in. So a watershed, for those of you who don't know, is basically just a region like here. When it rains in this region, the water is just going to flow from all these surfaces down to the river, eventually exiting the system. So the city says, okay, we got problems in these neighborhoods, let's solve them. So they go into a neighborhood, install one of these ponds, cool. Go into another neighborhood, install one of these. And that's all we can do. We can't afford massive projects, so we're going to spend the next 20 years, 50 years fixing a little bit of the system at a time, right? Not really how we design engineering systems. Not from scratch. We're just continually fixing this thing piecemeal. And the idea is that if you do a good thing here, a good thing there, and you do it everywhere, it's somehow going to improve the system. And when we first started working on this problem, originally we said, is that actually true? Like, if you keep fixing little bits and pieces, is that fixing everything? And the answer we found wasn't just surprising, it was kind of shocking and a little bit terrifying. So what I want to show you is two neighborhoods right here. So let's say we have these two neighborhoods. And I promise this is the extent of plotting that I'll do here. But let's say this is time right here. And what I'm going to do is I'm going to hit these neighborhoods with two storms. So one storm here, another storm here, and I'll plot the water level. So what you'll see is in one neighborhood, the water level goes up when it rains, right? And it's very fast. The water goes in, the water goes out. That's how we design it, just like here in LA. Another neighborhood, and what you'll see at the end of the watershed where we might have flooding, for example, they add up. So they're not on top of each other. They're separated, and just gives us this behavior. So now you have flooding in these two neighborhoods. You install one of these systems. You improve one neighborhood, see, it looks much nicer. This is how we decide in engineering. It's like subjective, like, oh, that looks better because it doesn't flood as much, right? It doesn't go up high. We fix it in one neighborhood, we fix it in another neighborhood, but we didn't think about the system as a whole, and now they're actually adding up to give you worse behavior than you had before. So not only are little fixes not leading to better fixes overall, they might be making things worse. And so that's really kind of scary, actually. So this is where technologies come in. And this is a slide I always show. I teach a class on sensors, actually, this semester. And I always like to show the students how far we've come even in the last decade. With the ability to take measurements sort of locally to things. This is a temperature and humidity sensor that's teeny that we can basically just deploy right now, and we use these all the time. And the ability to take these kind of measurements has been accompanied by really a big revolution in the ability to sort of locally compute, so microcontrollers and all sorts of little processors, and send that data to the internet. Right? So now we have sensors, we have the ability to communicate that, and it's slowly ushering in a new way to look at water systems, a new way to sort of measure them. And this is reshaping a lot of different areas of water. I'm going to show you the drinking water ones because this is where it's really taken off right now. But these are leak detection systems in cities where you can see like an operator could go and check on where the leak is. And they're also making it to your house. So you can go on Amazon right now and order this little smart irrigation widget that basically waters your plants for you, right? Saving water. The one I want to focus on today is that sort of the forgotten infrastructure, stormwater. So this is a picture that we came up with when we first started talking about this, and it's this idea of, in the time of a smart city, what are smart stormwater systems going to look like? Is that even a thing? And so if you imagine a city that's blanketed in sensors, you could have something like soil moisture sensors, rainfall sensors. You could be taking in water quality, radar data, to really understand how this thing functions as a system. Right? That's what I was talking about. So you take that measurement. And then we say, instead of just measuring and being discontent with how the system functions, can we actually change into real time? So could we basically add valves and pumps and gates to really reconfigure the infrastructure in real time? So instead of relying on upgrades that happen every couple of decades, can we reconfigure the infrastructure on a second-by-second, minute-by-minute basis? And the conceptual idea would be that we go back to those two neighborhoods that are adding up and causing flooding downstream. I could, for example, go in. I had this flooding problem. If it's raining more in this neighborhood than this neighborhood, I could add 2 valves to it, hold water accordingly. I can find storage in the system and basically taper it out so at the system scale it's actually achieving the kind of benefits that we want to achieve. So really this idea of, this is kind of what we mean when we talk about smart water systems. And when we first started talking about this, we basically needed to show to people that this actually is going to work. And so we like to build a lot of widgets in lab, and this is one of our examples. So here you see what we call our sensor node. This is basically a stripped-down cell phone. You take your cell phone, you take away everything except for the processor and the cellular modem, and now you're able to basically add a bunch of sensors to it. So you can measure things like rainfall, soil moisture, depth. You put it together, and now this thing is connected to the internet and sending you data. And usually we deploy them in like 1 per square mile. Sometimes you might have many more per square mile. And now we can get a real-time sense of what's happening in the system. And once we know what's happening, we can start adding actuators. So these are gates and pumps and random things that we can use to change the flow of water. All of these are open source technologies, so that was one of the goals from the beginning, was to sort of say, not just a black box, but this is how we do it, right? We wanted to convince cities to do it. We built a whole cloud infrastructure that allows you to send sensor data from the watershed to operators who can then decide, if to fix their system or maintain it. But similarly, we can also send commands from that operations room to valves and gates to basically reconfigure the infrastructure in real time. And so the kind of things that this allows you to do is to start building just giant measurement networks. So here's an example of Dallas. If you've been following the news, Dallas has had some catastrophic floods. What we did here is we just tossed out 40 of these nodes, and these are actually really low-cost nodes that we put out there. They're measuring flooding in real time, and they're hidden in the urban landscape. Oftentimes you can't even see them unless we point them out to you. And they're sending data back in real time. That's the intent there being to send out warnings to motorists and other people who might want to be going around flooding, right? So real-time flood forecasting networks. And while these measurements are going to sort of enable all sorts of stuff like this, we really think that the potential is going to be in control. So we decided a while ago, we were sort of measuring the system, saying, can we actually change it? And this is what we came up with. Nothing earth-shattering, it's a valve. But we basically took this valve, hooked it up to our internet-connected device, and now we can change when we want to open and close it. And this shows you one of the sites. So this isn't a neighborhood that we're working in. This is just a regular stormwater basin. You've seen them everywhere. By closing that valve, we decide when the water is going to be in there and when the water is going to leave. And so it basically completely allows you to reconfigure this stuff in real time. And what we've been trying to do with these kind of technologies is we've been trying to sort of scale them out. And we have some foundation support to do this. The one I'm going to tell you about today is in Ann Arbor, Michigan. And so this is our network. So this is the watershed that I was telling you about earlier. So it's about 10 square miles. And when we first started working on this, we didn't know how many sensors were needed. There was no blueprint for this. So we just decided as many as we can afford. So that's kind of what we did. So we went in there, and we started littering this thing with sensors. Like in some places, we have like 15 per square mile, just, you know. But the point is, it's going to lead us to the answer that says this is how many you need. We have valves in the system. We have water quality sensors, soil moisture sensors, really sort of just like trying to figure out what's happening in the system through these measurements. And we have a lot of these control sites as well. So this is one of our first control sites. We worked with the city and the county to add valves to the system. This is a 5 million gallon stormwater basin. And what you see is the students basically deploy these valves, and you can remotely send a command through the internet or automate it to basically decide when you want to release the water. So this is what it looks like when you open up the valve. Water's not coming out fast, and that's because we want that, right? We don't want it to come out fast. We can control how quickly the water is actually going to exit these systems. So you can optimize the performance of this one particular asset to do basically what you want it to do within some limitations. So a lot of benefits you can get are just holding the water back, which captures all these sediments in the water that trickle down, and so they don't go down in the river. You can help with local flooding, but it brings up this idea, again, of now we can really optimize local performance. Does that mean we're actually doing way worse at the watershed scale? So the thing that we wanted to do is to say, can we start operating this basin to try to sort of help the bigger watershed? And what we did is we sort of zoomed out on the map and we said, okay, here's our basin. It's 5 million gallons, so it's kind of a lot for a bunch of students to have a push button on. So I still can't believe the city let us do it. But so 5 million gallons, and this is how the system usually worked. The water would flow downstream, and it would flow downstream to this wetland. And so for those of you who might not be familiar with it, a lot of green stuff, a lot of these green parks and stuff in cities are actually designed to treat water before it goes out. So there's a lot of microbes and a bunch of other plants that are actually treating the water. So what happens during any regular storm, if it's small enough, the water will basically go from here and a bunch of the other areas and it'll flow through this wetland before it goes out into the river. Now, most storms end up being way bigger than what this was designed for. So what you actually see in most cases is this thing overtops and this neighborhood ends up flooding. So the idea, the simple example that we wanted to carry out was basically this idea, could we put a sensor downstream and just only send water when this thing can actually handle it? And now, this is about 2 miles apart. Okay, so a bunch of students basically doing this thing 2 miles apart. We're going to try to see if this one can influence the one downstream. And here it is. So this was December of about a year ago, I think. And what we did is we had a storm, we closed the valves, and then we just waited. We waited for the downstream to flush out. We were looking at the sensor reading. And then when we said, okay, that wetland is ready now, we can send the water down, we turned it on. And so what you see here is the basin is basically opening its valve, it's going down, and about an hour later you see the wetland water levels rising. So when we first started showing this data, a lot of people were saying, like, well, is that really happening? Because we're using measurements that people aren't used to normally. We're using cheap measurements, right? And so then we figured out, okay, if they don't believe us, we've got to like take videos, and that's what we started doing. So here you go. So there's a video, the water levels are going down, you see it decreasing. And now I'm gonna transition to that downstream basin, and I'll show you this downstream basin. So here you go. It's sitting there, and the water levels are slowly going to start rising. And because it's not raining, we know that the only thing that could be driving this is actually the control from upstream, 2 miles away. And so it's kind of amazing because basically that says we can control things that are really far away and we can start achieving these system-level benefits. And these benefits, as it turns out, are actually compounding. So here, just to show you sort of what one valve does. Okay, so you have this basin, it's 5 million gallons. First, you hold that water for 48 hours or 24 hours, which settles all these sediments, so you get a water quality benefit. Then you're improving localized flooding performance. And then when you send that down, it's actually now going through this wetland as opposed to bypassing it and flooding. And now you basically get this cascade of benefits from just a single valve. And this, for us, was a really big milestone because basically it showed us that this is possible, right? It was like step one to showing us that this is possible. And it led us to the next question, which was, okay, if we can do one valve, what happens? Actually, somebody asked us, what happens when you get a big watershed? So when you scale out to 10 square miles, how many controllers you're going to need, what are you going to do? And that's the point where the city is going to say, no, like you can't put all these valves in there. We're not going to let students sort of play around with this. So we said, okay, let's try to simulate. We were talking about simulators earlier. So what we've been working on is sort of, this is really where the research is for us, is this new generation of algorithms that take what we know about water system, simplify it down to what we need to know for control, okay, so like simplified systems, and then we can start applying algorithms, we heard it earlier, from self-driving cars, from dynamical systems theory, from all these different things to start controlling the water flows. And this allows us to basically look at these systems and start playing these games in a virtual world. So here we have, again, this flooding, like water goes up and then it goes down quickly. Can we create situations like this where the system is basically just going up, staying steady, and going down? So that's really good because you're basically reducing flooding and there's all sorts of water quality benefits from this. And so it works in the computer world. but then we wanted to say, okay, does it really work in the real world? So we wanted to apply this, and we looked at this watershed. So I keep coming back to this watershed because that's where we're working. This is the outlet of the watershed. We wanted to see if we can create this control. We wanted to go from this to this. Okay, so that's what we did. We applied these algorithms, and here's a bunch of our data. And again, who trusts our data? We said, okay, can we go to a data source that people are really going to say this is like actually happening? Here is a USGS gauge. So for those of you who don't know what the USGS is, it's the United States Geological Survey, for those of you. They are one of the main agencies that's responsible for monitoring water across the United States. They deploy stream gauges, which are basically these sensors that measure water flow. We're really lucky to have one in Ann Arbor. They're pretty pricey, but we have one at the outlet of the watershed. And basically what we said here is, look, the USGS gauge is picking this up. Okay? Across 10 square miles, whatever we're doing here, the USGS gauge is showing that the water level can go up. We can control it to stay steady, and then we let the system drain. Okay? So that was like being picked up by federal measurements. So we're like, okay, this has got to count this time, right? So, and then we said, okay, well, that's possible. I told the students, like, well, what do you guys want to do next? Like, what should we do? And I walked in the lab one morning, and I saw this, and I was like, what are they doing? And it turns out they were trying to spell the logo for our school in the actual water surface. So they're spelling the block M. So there's a poor person at USGS who's probably looking at these water flows and going, I think somebody's spelling their name or something worse in the water. Anyway, so you let some students loose and they come up with stuff. So that brings me back to the thing I was saying earlier. Okay, so like, what role are these technologies going to play? It seems like a silly demo, like why are they spelling letters? When you show this to the city, they can see, okay, if you can spell a letter, you can do something much more meaningful, right? And that's kind of where we're going. And so going back to the question of what are these technologies going to do, the thing that we're trying to sort of say now is we're going to say that when you add these technologies to existing infrastructure, they're basically going to shrink the size of the infrastructure that you need to deal with things. And so conceptually, this is one way to think about that. Let's think about storms. A storm can be really short or really long, and a storm can be basically really small or really big. So intensity versus duration. And you would imagine that any normal system would have a breaking point, right? So like if a storm is too strong or too long, it's going to flood your system. And so basically you're going to end up with things like this. And the thing that we're saying with basically this kind of paradigm is that adding control is going to push the performance of your system. You don't need to build new stuff. You can actually use what you have in a much more effective way. Flip side of that being is if you need to build something new, you can make it much smaller. And some of the simulations that we're running right now are basically showing us that you can build infrastructure at half the size and achieve the same kind of performance, which is really exciting. Because these valves are really cost effective. I mean, that valve I showed you costs like a couple $1,000s, so not that expensive. And so that kind of brings me to, like, you guys are in the room here. What are the opportunities in this field? I think we're just scratching the surface of all of this. And I kind of try to think about like the three things that I think are sort of important at the moment. And they split up into three categories for me. The first one is obviously engineering, because we're here at the National Academy. We have to figure out how we can take knowledge about water systems, like decades and possibly a century of knowledge about how water systems function, and embed it in a new generation of control algorithms. We still haven't figured that out entirely. I mean, we're working on it in the lab, but there's a lot of work to be done there. And that presents a really amazing opportunity because we can engage with colleagues, like from civil and environmental engineering, we can engage with colleagues in electrical engineering, computer science, mechanical engineering, control theory, et cetera, to try to build these systems. And so that presents a really big opportunity and sort of is going to push us to this frontier of building control systems for entire cities. The second thing, and I think this is actually to me the most important one and the one that I'm least qualified to address, and I think it goes to one of the questions that was asked earlier. A good engineering system is one that's efficient and low cost, right? Or I forget the phrasing. It's not quite how cities think, right? So efficiency and cost are not the only things. And the water sector in particular is very risk averse, and understandably so, right? Because one small mistake can lead to massive ramifications to human health, human safety, et cetera. So we got to figure out how to engage decision makers. We got to figure out how to engage residents. Our way of doing it is just like inviting them and saying, hey, come check it out. It's just a solar panel and a valve. It's fine, right? But we got to figure out how to get them to trust these systems and convince them that these could be viable solutions compared to how things are traditionally done. And again, this presents a really cool opportunity for us as engineers to engage with people in social science and economics to really try to sort of like project the value of these systems and try to figure out what role they're going to play in communities. And sort of finally, I think one of the big opportunities is, for you all out here who are thinking about what you're going to major in. I had this really good discussion at lunch with a couple of you, and you're talking about you're trying to decide on majors. And that's always a specific thing, like I want to do mechanical, civil, electrical, et cetera, right? A lot of problems that exist out there can't be solved by just one discipline, right? Like, think about this one. You can't just know about water, can't just know about technology, can't just know about control algorithms. You really have to have a holistic process by which you think through and solve engineering problems. And I think some of the really exciting problems are going to be at that intersection. I think for us as educators, that means we have to create educational programs to provide you with that kind of education. Dan and I, didn't mention it, Dan, we were in grad school together. We actually sat next to each other. We had different advisors, but that's what we did. Our advisors said, well, we were in civil engineering. They said, go to the other departments and take classes, and you can see what it leads to. He works on traffic, I work on water, but at the end, it's coming together. And so I think that opportunity is there. I think another opportunity that doesn't get talked about a lot is the ability to educate a new generation of engineering technicians. Not everybody has to go to college, right? There's the opportunity to actually get a really rewarding career that includes this kind of techie thing to it, but people are going to have to go out and they're going to have to replace batteries and they're going to have to maintain these systems, and I think that opportunity is there, and it's another really good opportunity to sort of promote equity and inclusion within engineering. So with that in mind, I just want to close and say that none of this would have been possible without these guys. So everything I showed you today was deployed by university students and high schoolers, actually. So we have all of them working out here, and a bunch of their photos are on here. Everything you see here is on this website, openstorm.org. It's our open source portal. You can take our plans and put it in your own city, but the thing I'll tell you is that it's way easier to build the technologies than it is to convince some mayor to let you actually deploy it. So that'll be up to you. And with that in mind, I'll be happy to take questions.